We've been talking about aerial sweep efficiency, and now we're going to be talking about vertical sweep efficiency. So, a little bit of background. We know that the dimensionless oil recovery is ED, EA, EI times SOI minus SOR. And the reason that this isn't 1 at any given time is because of 4 different reasons. We effectively have 4 kinds of oil left behind in a reservoir. One of them, a little fuzzy here. Let's see if we can. There we go. So there's really 4 kinds of oil that's left behind. One of them is SOR. SOR, unless we inject something like our surfactant, is going to be there forever. We can't get it out. It's trapped because of capillary effects. And you can see that in a relative permeability curve, for example. We haven't talked much about that, and we probably won't. This is more of a petrophysical type property. There are some enhanced oil recovery classes here that you could take. You can learn more about how you might be able to recover that, but it wouldn't be with a traditional water flood. Then we talked about the displacement efficiency, which is time dependent. And what displacement efficiency is, it occurs in 1D, and because it occurs in 1D, it also occurs in 2D and 3D, but it was easiest to understand it in 1D. And that is the oil sweat that gets trapped behind. And if you plotted things like SW versus distance, we know that you plot like this, and this is the oil that's bypassed, right? We call that the displacement efficiency is related to how little we leave behind that's bypassed. Now this amount of bypassed oil will change with time. It will decrease with time. You'll recover more and more of it, as are with these other efficiencies. Then we learned about, so this is ED, then we learned about EA, which occurs in 2D or 3D. And that had to do with the aerial sweep around. So at certain times you'll have unswept oil over here and over here, and that's related to aerial sweep efficiency, and we learned how to do some calculations of that. What we haven't talked about yet is vertical displacement efficiency, and that's EI. And that occurs in 3 dimensions, or anytime you have vertical layers. And so let's say you had a reservoir, and now it's got layers. And this is typical, right? So you've taken some geology classes, and you probably know that because of depositional environments and whatnot, that you can have different layers of different permeabilities. So this might be K1, K2, K3, K4, and K5. And maybe this is filled with oil and the only water present is irreducible water, for example. And you inject water over here at the injector and you produce over at the producer. Well, what happens? As usually the case, fluid likes to go through the path of least resistance. So let's say the 3rd layer was the most permeable. Well, water would probably invade all 5 layers, but it would especially invade the 1st layer, right? I mean the 3rd layer. Okay, it would want to go in the lowest resistance path. And we know Darcy's law says that velocity is proportional to pressure gradient. But if you've got a higher permeability here, that velocity is going to be higher for the same pressure gradient. So that water is going to want to go into the path of least resistance, or the path that has the highest permeability. To make matters, and then what happens is that you can have a snowballing effect. So what I mean by that is that if you're injecting low viscosity water if you're injecting to replace high viscosity oil, then this becomes even lower resistance, right? Because now you have this lower viscosity fluid, and we know that you have permeability divided by viscosity. And so what that means is that this sort of compounds on itself, or it's like a snowball effect, right? It's like a snowball rolling down a mountain. It gets bigger and bigger, and so you have more and more water come over here. Less of the water goes in these other layers. Eventually you get breakthrough over here, and then you really have this low resistance path just for water to flow. And that's not particularly what we want, because then we're leaving behind a lot of oil in these other layers. We refer to that as being vertical displacement efficiency, EI. And it is a number that goes from 0 to 1. It does increase with time. So eventually water would displace all, all the movable oil in those other layers. But this is vertical sweep efficiency. EA was aerial sweep efficiency. And just so you know, sometimes we combine the two and we call it volumetric sweep efficiency. So to understand this better, clearly heterogeneity has a big effect on vertical sweep efficiency. And so we'll need to understand heterogeneity a little bit. Now, many of you are in geostatistics or have taken geostatistics, in which case some of the things I'm going to talk about are very much a review. In fact, you probably know a whole lot more than what I'm going to explain. I'm just going to talk about just the basics. But it's important that we recall that, and there are some of you that probably have not taken geostatistics, so it's good to have that. So we are talking about vertical sweep efficiency now, and we've got, hypothetically these different layers. And, I've got that top picture over there, and that's like aerial sweep efficiency, but this vertical sweep efficiency, kind of like I drew on my piece of paper just a moment ago, you have these different permeabilities, which means the water invades at different rates. And so in this case, the first top layer is almost certainly the highest permeability, and it's getting over there, and it will break through before the other layers do. That's not ideally what we would want. We would want everything to kind of sweep through all the layers at the same rate, and then push through, and then get your recovery. But that's not how nature and geology work. I won't go through this too much because we just talked about this, but again, this is the formula. This is a slide I keep coming back to, and it describes our oil recovery and our 4 different mechanisms for leaving oil behind. And we're going to talk today about this vertical sweep efficiency effect. So let's talk a little bit about geostatistics and heterogeneity. I'll start out really simple. Petrophysical properties, and there's lots of them, but permeability and porosity are the easiest to talk about. We'll talk mostly about permeability. Are not uniform in a reservoir. I think you all know this by now, whether you've taken the geostatistics class or not. Permeability varies throughout the reservoir, and these reservoirs are huge, and they can vary in terms of for permeability by orders of magnitude. And so if you made a plot of permeability field in a reservoir, it might look something like that. And I don't have a scale color bar there, but maybe the red regions are very high permeability and the blue regions are low permeability. You can even see that this is sort of layered in here, right? So you have a low permeability layer right here and a higher permeability layer on top. And so you can visualize that. These are just 2 pictures I have of porosity, and these are sort of histograms, right? So they're like bell curves. This is a porosity, and so you can see in this particular sample, it goes from 0% all the way to 17%. That's somewhat typical. It's on the low end, but somewhat typical. This is for a gas field, and you can see that the peak here is right around 5 or 6%. So most of the average is going to be in that range. Then here's another plot, but this is a permeability. Now, importantly, permeability is not usually a normal distribution. It doesn't follow a normal sort of bell curve. It is a log normal distribution typically. And for that reason, we plot the log of permeability on this axis versus the frequency And that does, when you plot it with log of permeability, it looks like a normal distribution. And so the mean is somewhere over in here. And so typical values of porosity are 15 to 20% for, say, sandstones, maybe some carbonates. For shales, they're considerably less, right? There can be just a few percent. Permeability varies a whole lot. It varies from reservoir to reservoir. It also varies within the reservoir. So a typical reservoir, maybe a sandstone reservoir, might be from 1 to 1,000 millidarcies in different parts of the reservoir, right? Depending on what layer you're at and different location that you're at. And again, it's such a big range that you do a log of those and you make these types of plots. Now this might be for one reservoir. You could have a carbonate reservoir that had a lower permeability and it might go from 0.1 to 10 or something. Of course, a shale reservoir, those are going to be on the orders of like nanodarcies. A little bit of review of statistics. I'll start out really simple. Let's say you have a sample of n samples of some petrophysical property. And I'm calling it phi here. If you want, think of it as being permeability or porosity, either one, or it could be another petrophysical property. If we wanted to know what the arithmetic mean or average is, that's super simple, right? We've done this our whole lives, is that you just sum up all the properties and divide by the total number. So if you wanted to know the arithmetic average of permeabilities and you had 10 samples, like say 10 different rock cores, and you measure the permeability of those, you'd add them all up and divide it by 10, and that would give you the average permeability. Now that's the arithmetic mean, but there's also other means. Another one is the geometric mean. The geometric mean is, this symbol here is a product, right? Whereas this is a summation. This works just like it, but it's a product. And you multiply all the values, and then you take the nth root of it, okay? So let's say you had a permeability of 2 millidarcies, 5 millidarcies, and 10 millidarcies. Well, you do 2 times 5 times 10 and take the cube root of that to get your average. Now the average should always be greater than the minimum and less than the maximum, but you'll get a different answer over here. There's another way to do this, and that is to take the logarithm of both sides. If you take the natural logarithm over here and the natural logarithm over here, then our rules of a logarithm say that this 1 over n could come out in front, and then when you do the ln of a times b, it's equal to the ln of a plus the ln of b. So because of that, if you do a natural log is actually an arithmetic average of the natural logs of the property. So it's 1 over n times ln of the first property plus the second all the way to the end over there. So this geometric mean, if you write it in terms of natural logs of the values, is actually an arithmetic mean. If you don't quite see that, then maybe prove it to yourself by working through it. That's the average, but we're talking about heterogeneity. And what we mean by heterogeneity is how much it varies throughout the reservoir, right? How much the sample varies. So there's a difference between if you take 2 exams and you get an 85 on both versus if you get a 70 on one and a 100 on the other. They both have the same average, but they have different variability. In the first case, there was no variability. You got exactly the same score, but in the second case, it varied quite a bit. The variance, we're going to use the symbol s squared, is defined as 1 over the sample size minus 1. So if you've got 10 samples, then it's 1 over 9, times the sum from I is equal to 1 to n of your property. So this could be all your permeabilities minus the average, right? And so if we go back to the example of my exams in a second ago, maybe if the average was an 85 in both cases, then you do a sum of 85 minus 85, that would be 0. And then you'd add 85 minus 85, that would be 0. So the variance is 0. Well, we kind of already knew that, right? You got exactly the same score as no variance. But if you had 100 and then you had a 70, then 100 minus 85 is 15 squared. And then you had 70 minus 85, which is minus 15 squared. Then that's a big number. So the variance would be high. We also talk about the standard deviation. The standard deviation is simply the square root of the variance. So whereas we call the variance S squared, we'll call standard deviation S, and we'll take the square root of that to find the standard deviation. That is kind of sort of standard statistics. So if you take any statistics class in the math department or anywhere, those are the kinds of things that people will talk about. Of course, there's other statistical properties out there. When we talk about geostatistics, when we talk about petroleum engineering and reservoirs, the Dykstra-Parsons coefficient is a really common way to describe the variance. And it's related to the variance and standard deviation we talked about, but it's defined in a very specific way for us. And you could do this for any variable, but we usually do it for permeability. And so it is defined, the Dykstra-Parsons coefficient is defined as the permeability, I'll just put this, the permeability value which 50% of the samples are greater than, minus the permeability value that 84% of the samples are greater than, divided by the permeability at which 50% are greater than. So what you might do is you might get a bunch of permeabilities, and these could come from rock cores. They could come from well logs as well. So you all, many of you are taking well logging, but you could get the permeability at a bunch of different locations. Maybe these were at several different wells or something. You measure the permeability, and then you make a plot. So on the y-axis is the permeability on a log scale, right? So in this case, it looks like the permeabilities vary from, about 1 millidarcy to about 10,000 millidarcies. And then on the x-axis, this is the probability of samples that are greater than that permeability. Okay? So what this says right over here is that if you look at them, about 100% of the samples have a permeability greater than, less than 1 millidarcy, right? Over here, 0% of the samples have a permeability greater than, say, 15,000 millidarcies. Come out over here, it looks like, well, we wanted K50, so you come over here at 50, so right around over here, that looks like about 50% of the samples have a permeability greater than, say, 200 millidarcies. 84.1, that's probably somewhere around over here, and it looks like, I don't know, I'd have to look at it closer, but 7 or 8 millidarcies is the permeability that have a probability greater than that. And so you do this calculation based on your sample data, and you will get a number between 0 and 1. You won't get anything negative, you won't get a value greater than 1. A perfectly homogeneous sample would have a Dykstra-Parsons coefficient equal to 0. And that makes sense because the same number of samples would have a permeability at which 50% are greater than as 84.1%. So you'd have, your numerator would be 0 here. This would be a completely homogeneous sample. The permeability is exactly the same for all of them. On the other end of the spectrum, if you had a Dykstra-Parsons coefficient of 1, that would be very heterogeneous. Usually we don't have reservoirs in those two extremes. Typical values are 0.5 to 0.9. 0.5 is still pretty homogeneous. Maybe a loose gravel pack, a loose sand pack or something would be like 0.5. 0.9 would be a heterogeneous carbonate or something. Understand that. So Dykstra-Parsons coefficient, very common method for measuring heterogeneity. Another one is the correlation length. Now, this is important for geostatistics. So it's not just the variance. Okay, when we talk about variance and heterogeneity, things could be randomly placed throughout. So if things were perfectly random, then the permeabilities would be scattered randomly at different locations of the reservoir, and there would be no, and we're calling it correlation length, there'd be no correlation between the scales. That's not what happened, you know, and there are some physical phenomena that are completely random, but geologic processes are not usually. There is what's called spatial correlation. So what I mean by that is that if you have relatively high permeabilities in one part of the reservoir, let's say you took a sample from a well at one location of the reservoir and it was relatively high permeability, then if you were to take samples close by, they would probably also be relatively high permeability. And likewise, if you took a sample from a well far away and it had a low permeability, then any additional samples you would take in the nearby region would probably also have a relatively low permeability. There would be some scatter, they're not going to be the same, but they'll be correlated. And that's related to the geological processes that these reservoirs were created. We like to quantify that length, and we call it the correlation length. We're going to use the symbol gamma, and it is a function of distance. Okay, so h is sort of the distance away, and we measure that by the sum of our samples from I is equal to 1 to n of our permeability at one location minus the permeability at a location h distance away. And we're going to square it and we're going to divide it by 2n. So what you probably are going to get is if h is small, then this number is going to be small, right? The permeability here is going to be pretty close to the permeability if it's spatially correlated, right? So if h is 10 feet, let's say, and you took a permeability in one place and it was spatially correlated and it had 200 millidarcies, which is relatively high, then 10 feet away, it's probably also going to be relatively high. Might be 220, might be 180, but it's probably not going to be 1 millidarcy. If you go far enough away, if you go to h is equal to 1,000 feet, then these two things are not going to be correlated at all. Okay, whatever the permeability is here has almost nothing to do with the permeability there. If you make a plot of this, and again, you're going to have some sort of data, right? You get your permeabilities, maybe you've got 20 wells and you had 20 core samples and you went into the lab and measured the permeabilities, then you could do this calculation. And the y-axis is called the variogram, and that's just this gamma variable here. And this is the distance, or h. And if you make this plot, then it looks like this. Now, you're going to have, when h is 0, this has to be 0. So it goes right over there. Sometimes there's an immediate jump in that, and we call that a nugget. And if you make this plot, then you'll get something that looks like this, is that up until this distance, this is changing. And when it's changing, that means it's still correlated. Once it gets to this distance, gamma is constant. And what that means is that they're uncorrelated. So roughly speaking, this position where you start to see no more correlation, this distance from here to here is the correlation length. Maybe it's 10 feet, maybe it's 100 feet, maybe it's 200 feet, but eventually you get to a point where they're so far apart that there's no correlation anymore. And by that, again, I mean that there's really no relationship between the two. So if you have a high permeability in one location, that's in no way indicative of what the permeability is 1,000 millidarcies away, or 1,000 feet away, or at least not much of a relationship, right? So maybe that's got the same permeability, but maybe it's got a lot less, or maybe it's a lot more. There's just, they're not correlated. So there is another measure of heterogeneity, which we'll talk about, which is the flow capacity and storage. What that is that this is particularly true in layered reservoirs, and this is just a schematic over here, that we have, let's say, 5 layers, all right? And each of those layers have a different permeability, and they have a different porosity, and they might have a different thickness of the layers, okay? And we're going to define the front velocities as being the permeability divided by porosity over there. Okay, and so you do this, and maybe R3 is the highest. So what you can do is you can reorder those, right? You might want to put the greatest at the top. So this one, K over phi, is the largest. So you make this number 1, and the second one number 2, this one number 3, this one number 4, and this one number 5. I haven't given numbers, but I'm just saying that's what it would be. And then you define some variables here. So little f of I is what we're going to call the fractional flow capacity of layer I. Okay, fractional flow, we talked about, this is similar to the fractional flow we've talked about in the past. It's the fraction of the flow, right? So it's going to be a number between 0 and 1. It is the flow rate in layer I, right? So f of I is layer 1, layer 2, layer 3, layer 4, layer 5. It's the flow rate in that layer divided by the total flow rate. So the sum of all the flow rates, right? So it's Qi over that. And you can relate the flow rate in terms of Darcy's law, right? So you got permeability and viscosity and all that. Well, let's assume that they all have the same viscosity and the same pressure gradient, but maybe they have different permeabilities and thicknesses, in which case this formula is Kh, everything else cancels, of the layer I divided by the sum of Kh of all the layers, right? Then you can have the capacity of that layer, okay, the storage capacity, basically how much pore volume is in there. So by definition, it's the pore volume of that layer divided by the sum of the pore volumes. What is the pore volume? It's the area times the porosity times the thickness, but they all have the same cross-sectional area. They just have different porosities and thicknesses. So the numerator is porosity and thickness of layer I. The denominator sums up over all the layers. Okay. Then we are going to define the cumulative flow capacity. So all it really is, it's a cumulative flow capacity of layers faster than I. Let's see if I can try to explain that. So you have several layers, 5 in this case, and you wanted to look at layer 3. Okay, remember we reordered this. So we had layer 1, 2, 3, 4, and 5. 1 we're going to order at the top. That was the fastest, and then 5 was the slowest. So when you do that ordering, the question is, what is the cumulative flow capacity of layers faster than layer I? Let's say we're interested in layer 3, so I is equal to 3. Well, what you do is you sum up from j is equal to 1 to 3. You don't go all the way to 5. You go from 1 to 3, and the denominator goes from j is equal to 1 to 5. So that's how you get this capital F. Capital C is a cumulative storage capacity, and it works in a similar way. So it's really the sum of these little cj's from j is equal to 1 to I, or you can write it in this formula. That might be a little confusing, so I'm going to do an example problem real quick here. We got 5 layers, just like we had on the PowerPoint. Porosity of those layers is 15%, 10%, 25%, 5%, and 20%. The permeability in millidarcies is 50, 10, 500, 1, and 100. Like a side note here, just looking at this, there doesn't seem to be much correlation in these samples, right? So these are different layers, these are different depths, but you know, this is medium, low, high, low, medium again. So I bet the correlation length was relatively low here, but I don't know. But these are in different layers. So within a layer, they're probably very, very correlated. So within the layer, they'd be correlated. So maybe the correlation length is about the thickness, which in this case is 5 feet for all the layers. We're going to define this velocity Ri as being k over the porosity. So it's going to be 5 divided by 0.15, and that's 333.3. 10 divided by 0.1 is 100. 2,000. 20. 500. And then if I do the reordered index, this is the highest, the third one, so that's number 1, right? 2,000. Next highest is 500, so that's 2. Next highest is this one. This is 3, 4, and 5. Okay, so I'm going to order them from the highest R to the lowest R. And so let me just do that so I don't make any mistakes. I'll do the layer again. 1, 2, 3, 4, 5. I'm going to put the permeability times the thickness. And that is 2,500, right? Because layer 1, which was layer 3, is going to be permeability 500 times thickness is 5. That is 2,500. This is millidarcies feet is the units. 500, 250, 50, and 5. So 5. VH is 1.25, 1.75, 0.5, and 0.25. Okay. And what I want to calculate is my capital F and my capital C. Let's go back to this, our slides here, and I can see for F, on the denominator, I got the sum over all samples of KH. And for the C, the cumulative storage capacity, I've got the sum over all samples of the porosity times the thickness. Okay. That means I've got a sum over all samples. And all that means is I just add up all these. So 2,500 plus 500 plus 250 plus 50 plus 5. That is 3,305. Likewise, if you do this, 1.25 plus 1 plus 0.75, etc., is 3.75. So these go in the denominator of the F and the C. But what about the numerator? Okay, let's go talk about that for a moment. So F, the numerator, is the sum from j is equal to 1 to I of my KH values. So if I is 1, I just do KH of 1. If I is 2, I do the 1 plus the second one. Okay, what do I mean by that? Let's go over here. So what this is going to be 2,500 divided by 3,305. You can check my work, but I get 0.756. This is 2,500 plus 500 divided by 3,305. I believe that's 0.908. This is 2,500 plus 500 plus 250 divided by 3,305 is 0.983, 0.998, and 1. C works the same way. It's going to be the porosity times the thickness here divided by 3.75, and I get 0.33. Then it's 1.25 plus 1 divided by 3.75. I get 0.6. Then 0.8. 0.933. And then 1. Okay, when you get to the last layer, it's always going to be 1 because you're effectively summing, this is going to be 3,305 divided by 3,305, and this one's going to be 3.75 divided by 3.75. It's a summation of all of them. Let's see if there's any questions on any of this so far. Okay, so there's a question about the indexing. And it is confusing. Maybe the example helped some of that, but capital N. Okay, so let's look at your capital F formula right over here. So the denominator goes from j is equal to 1 to capital N. N is the total number of samples, so that's 5. So I goes from 1 to 5. So it's 1, 2, 3, 4, 5. Okay, or it's really, j goes from 1 to n. Okay, but the numerator goes from j is equal to 1 to I. What is I? It is the subscript on this f. So if we wanted to find f for the third layer, then I is 3. So j is 1, 2, 3. We don't do the 4 and the 5. So that's what the difference in the indexes on the summation are. What you can do with this is you could create a plot of F versus C. This is going to go from 0 to 1. This is going to go from 0 to 1. And the first thing we're going to do is we're going to draw a straight line through it. So it's a 45-degree angle. So this is F is equal to C. Then we're going to plot our data. So at 0.33, we're going to plot 0.756. 0.6 is 0.908. And so you might get plots that look like this. And if we connect the points, maybe real life we'd have more samples. You get something that looks like this. This is F versus C. Okay. We're going to define the Lorenz coefficient as LC is equal to this area, I'm going to call that A, divided by this area, which is B. LC is equal to A over B. You can calculate that area however you want. You can count squares or do whatever. I mean, we know that the area under the curve is an integral. The formula for that is actually 2 times the integral from 0 to 1. Right? It goes from 0 to 1. F dc minus 0.5. Okay, so you're basically integrating this whole thing and then subtracting off the area under here, which is a half, and that is the Lorenz coefficient. Now, for very homogeneous samples, cases where the permeability doesn't change much, the area of A would be really small. Okay, and if the area of A is really small, then you get a small value of the Lorenz coefficient. So it's different than the Dykstra-Parsons coefficient. You'll get a different number, but like the Dykstra-Parsons coefficient, if LC is close to 0, if it's small, then it's fairly homogeneous. If LC is large, if it's close to 1, then it's heterogeneous. So a value close to 1 would mean that this is a really big area. Now you can never have greater than 1, but LC is this area A over area B. A small area A with respect to B is homogeneous. A big area with respect to B is heterogeneous. And this is what I have on this slide here. So got this Lorenz coefficient. You have the integral over here. You can, if you have an equation or you fit an equation to the data, you could actually do the integral. Otherwise, you'd have to use like the trapezoidal rule or some sort of numerical integration technique. But it's effectively the area of A divided by the area of B. Again, value of 0 is relatively homogeneous, or is very homogeneous. Excuse me. And closer to 1 is very heterogeneous. So that is a very quick overview of statistics and geostatistics. It's not nearly as in-depth as to what you have learned or will learn in your geostatistics class, which might be taught by Dr. Perch. But maybe this is a refresher for you. If you haven't seen it yet, then you're sort of caught up to speed on what we need to know moving forward. The next 3 or 4 lectures, we are going to be talking about vertical sweep efficiency. And so having different permeabilities in different layers, that heterogeneity is going to result in our water sort of propagating through one layer or several layers faster than other ones. And that's what leads to poor vertical sweep efficiency. And we'll be deriving some formulas and things like that.